Welcome. In this video, we're going to discuss the derivative as a rate of change. And if you are following along for my Canvas course, this is normally the type of example that would be a warm-up. But the derivative as a rate of change is such an important concept that I wanted to walk you through it together, or I wanted us to walk through it together. So the graph below represents the growth in volume of a spherical balloon as the radius grows. So these are the kind of 3-foot diameter balloons that are popular at special events like weddings. What does the distance from R6 to R equals 12 represent? That's this horizontal distance here. What does that distance represent? Well, that represents the change in the radius of the balloon. What does the distance between V evaluated at 6 and V evaluated at 12 represent? Well, V of R is the volume of the balloon in cubic inches, and it looks like we put in the radius of the balloon to get the volume of the balloon. So V of 6 would be here vertically, and V of 12 is about here. So this vertical distance is represented, and that vertical distance is the change in volume of the balloon. Now let's sketch a line connecting these 2 points. That is those 2 points right there. You will need a ruler for this. Now that your line is sketched, let's write an expression that represents the slope of the line drawn between the 2 points, and we do not need to compute the slope. So that is V of 12 minus V of 6 divided by 12 minus 6. So I'm just going to leave that as is and not simplify it any further. In our own words, let's explain the meaning of the expression we found in part C. This represents the average rate of change in volume of this balloon as the radius expands, and that's between 6-inch radius to a 12-inch radius. So in your own words, please write down something similar on your own paper. I hope the concepts discussed in this video were helpful.